Still on part 1, and now let's do step 1, in which I weigh out between 0.1 and 0.2 grams of the ammonium oxalate compound and record the exact mass. Well, there's a picture of the balance with the ammonium oxalate compound being weighed, and there's the exact mass, 0.1883 grams. Now, some of you might have wondered why I'm writing ammonium oxalate compound. Isn't that somewhat redundant? Well, not really, because the bottle that I chose to weigh out, you can just see it in there, the ammonium oxalate, is ammonium oxalate monohydrate. In other words, for every ammonium oxalate that's in the solid, there's one water of hydration, water of crystallization, whichever particular phrase you want. Now that's really important because, of course, I've recorded the mass of my beautiful little crystalline compound that you can see in there as 0.1883 grams. But then I've got to go from grams to moles. And how do I go from grams to moles? Well, I have to divide the grams by the molar mass, and that molar mass has to incorporate the fact that there's, say, water in there. So one of the nasty little tricks that you'll often see sometimes is when you've got a ionic compound that has these waters of crystallization in there, you've got to remember that that water is part of what you're weighing out, and so has to be incorporated in the molar mass to go from grams to moles. So then I take that solid and I put it into a conical flask or an Erlenmeyer flask, depending upon which side of the Atlantic you are, and I'm going to add 50 cubic centimeters of water. Now, there's my 50 cubic centimeters of water that I'm measuring out using a 50 cubic centimeter or 50 milliliter measuring cylinder or graduated cylinder. And then I'm going to take another smaller graduated cylinder that only goes up to 25, and I'm going to add in about 10 cubic centimeters of sulfuric acid. Now you can see the meniscus there is actually up at about 11.5 cubic centimeters. Okay, and in a post-lab question, I'm going to be asking you to think about these volumes that I'm adding of the water and the sulfuric acid. Anyway, then I swirled it until all of the solid had disappeared. I didn't think there was any point in showing you a picture of me swirling until the solid has disappeared. Hopefully that doesn't disappoint you at all. So that was steps 1 and 2 for part 1, followed by step 3. Fill a burette with the KMnO4 solution and add about 10 cubic centimeters of this to my oxalate solution and swirl. So here's a burette into which I have added some potassium permanganate solution. Now you can see that there, that beautiful deep, well, of course there it looks almost black, but you can see up the edge there, this gorgeous purple solution. Now a lot of times when you do a titration, you need to give a background to the burette when you're reading it if you've got a colorless solution. However, the potassium permanganate, you can see very, very easily where that gets up to. So I'll let you read this for yourself and decide what volume of the potassium permanganate I have when I filled my burette. Now you might be asking why, if I fill my burette, why is there 2 point something cubic centimeters gone? Well, I did that so you can see the scale. Okay, so it's pretty much a filled permanganate solution. Now I'm going to add about 10 cubic centimeters of this to the oxalate solution and swirl. And when I do that, this is what my burette looks like. So again, it's an about 10 cubic centimeters. I started at 2 point something. I'm ending up nearly 12 centimeters left in there. So you can see start and the, at least for now, the end of the addition. Not very important, as we'll talk about later on, for you to know exactly how much of this we added, but do remember that we added it. And something, of course, that those of you who are very astute will notice is there's a big drop of permanganate left up here, which has not been incorporated yet into measuring how much has been used. So before I finish, I need to make sure that I get all the drops, especially big drops of permanganate, back into the bulk solution. So I showed you the burette with the nice purple potassium permanganate solution in it. Now here's the Erlenmeyer flask, or the conical flask, to which I added that potassium permanganate. So this conical flask contained the solid ammonium oxalate that I weighed out, then the 50 cubic centimeters of water that I added to dissolve up the ammonium oxalate. So I now have the oxalate ions floating around in aqueous solution. I then added to that about 10 cubic centimeters of sulfuric acid, so that's my H plus that's going to be in there. And then I just added about 10 cubic centimeters of the potassium permanganate solution, which means that the purple permanganate ions are also floating around in this solution. So it's all ready to go. In fact, because I've got the oxalate and the acid and the permanganate in there, it's already starting to react. Of course, the fact that it's purple still tells me that not all of the permanganate that I have added has yet reacted. Now, before I go on, I do want to point out something about the precision of glassware. This is a conical flask, otherwise known as an Erlenmeyer flask, that supposedly has 250 milliliter capacity. That little line there that you can just see is 250 milliliters. Well, this line supposedly represents 200, this line supposedly represents 150, and this line supposedly represents 100. So if you believed these markings on the graduated cylinder, you'd say, well, I've got a volume of liquid that's pretty close to 100. And of course, it's even closer than it looks because the flask is tapering as you go up. So if one was to look at this, I'd say, oh, I've probably got about 90, maybe 93, 4, 5 cubic centimeters of solution in here. Now you think about what we put in here. We put the ammonium oxalate, which we're going to assume hardly has any volume when it's dissolved up. We added 50 cubic centimeters of water, about 10 cubic centimeters of the acid, another 10 cubic centimeters of the permanganate. So we got about 70 cubic centimeters of solution in here. That does not match up with what this line means. And the reason for that is that these lines in a graduated, in a Erlenmeyer flask or a conical flask or a beaker, they have absolutely zero precision whatsoever. So really, I like to tell my students, ignore these markings. But if you are going to do it, it's just take it with not just a pinch of salt, but a very huge, big salt cellar, because they really have very little meaning. Anyway, moving on. I'm going to heat this solution gently to about 80 degrees Celsius until the color has disappeared. So I heat it up, and there it is. My color has disappeared. And all that means is that now all the permanganate that I added, that 10 cubic centimeters of permanganate that I added in the last slide, has all reacted up. So I've still got some unreacted oxalate in this solution. And now I'm going to go ahead and titrate that. Now I've crossed that out because I'm going to move to another slide, but I'm now going to add more potassium permanganate by titration, which means I'm going to add more potassium permanganate bit by bit by bit by bit by bit, so I can see how much I had to add to use up all the oxalate. So in continuing on, I've heated the solution. I've got that colorless solution I showed you. Now I'm going to resume the titration. And I've actually got a couple of teeny little videos associated with this just to show you how I do it. Okay, so first of all, I had my colorless solution sitting there. I'm stirring it nicely. I'm going to add a little bit of permanganate, and look, boom, look how quickly that vanishes, that color. A little bit more, vanishes. Where I add a little bit more, and this is a technique, notice I swirled that tap 180 degrees. I didn't open it by turning it 90 degrees and then closing it with another 90 degrees. I just added a teeny little bit by rotating 180 degrees around. Just like that. Now, I kept doing that, and my initial video of this lasted quite a while, but fortunately my extremely talented son was able to edit the video for me, and now here's towards the end of what I did. So I add a bit more. See how the color persists a bit longer? Add a little bit more. See how that pink stays there? It goes away, but now add a little bit more. And that's just perfect. Now I've added just enough of the potassium permanganate there so that now my pale pink color has persisted for 30 seconds. So I've added enough of the potassium permanganate to use up all of the oxalate, and somewhere in that last little teeny bit of the permanganate solution that I added, it used up the last of the oxalate, which means that the residual permanganate stayed in the solution, stayed unreacted, and of course when you have a little bit of purple diluted nicely, it is pink. Now then we say to record the total volume of the permanganate added. So back to my burette, and now you can see I'm down there a little bit more than 31 cubic centimeters added. So I started with that 2 point something that was on the first slide. I then added about 10 cubic centimeters of the permanganate, and then I added more bit by bit by bit, so that I've added in total 31 point something cubic centimeters. And we can use all that to calculate the concentration of the potassium permanganate solution. So we've finished our data collection for one trial of part 1.